Hello everyone, welcome to lecture 2 of week 5 on the course Power Network Analysis. In today's discussion, we will continue with our discussion on the module of transmission line parameter evaluation, but we will take up a topic which is new to this particular module, which is capacitance evaluation. In the previous few lectures, particular to module 4, main module 4 uh, uh, cover topic, which is transmission line parameter evaluation, we have discussed about what is resistance, what is inductance, how do we evaluate physically the values of resistance, be it DC resistance, AC resistance, what is skin effect, what is corona loss, and how do you evaluate the inductance using magnetic flux linkages. So we'll continue with similar discussion and understand how line capacitance can be evaluated for given three-phase transmission lines. That's the eventual purpose. So as I mentioned, we had finished up with our discussion of inductance of three-phase lines in the previous lecture. And similar to inductance, which is mostly attributed to a current carrying conductor reciprocating out magnetic flux lines, on similar lines, the same current carrying conductor also emanates out electric flux lines or field lines. So if magnetic flux lines or field lines are associated to inductance, the corresponding electric field lines or flux lines and their interactions would probably lead to capacitance. So in a layman perspective, capacitance is a property or an attribute defined or shown by two conducting mediums which are electrically charged, definitely having some non-zero potential difference between them, which indicates that there is some electric field in between these two conducting mediums. And these two conducting mediums, they are not electrically in contact to each other. In fact, there is a non-conducting medium present between these two conducting bodies which are charged and have unequal sort of charges on them, which sort of results into some potential difference between them. So this non-conducting medium, it could be a insulator, could be any other device which is not a good conductor. So if we have such a arrangement where we have two plates, two electric plates, and we keep them little spaced to nearer each other, not with a large space. And if we charge these two plates, the air in between these two plates can also act as an insulator, and eventually these two plates, electric plates, will also show the attribute of capacitance. So that's the basic layman definition. Air in between two transmission lines or air in between transmission line and earth also leads to a similar arrangement where we have two charged bodies or charged plates which are separated by air as an insulator in between them. So that is essentially the reason why transmission lines also show the attribute of capacitance. Capacitance in its very basic essence is has the unit of farad, which is denoted by capital F. It is nothing but per unit charge with respect to the voltage. So if it is charge is in coulombs C and voltage is V, the symbol is V, well said, the volts. So C is nothing but Q by V, and Q and V here, they can be instantaneous quantities, time varying quantities, they can be phasors, etc., etc. So from a electrode or a capacitor electrode perspective, Q is nothing but the charge in coulombs, and V is the potential which this capacitor can handle between these two electrodes. And as I mentioned, Q and V, they can be instantaneous values, they can be DC or AC phasors depending on what type of material element is attributing this capacitance property. So our entire discussion for line capacitance evaluation would focus on this basic evaluation. And in fact, for mediums which have absolute permittivity, unlike permeability for magnetic fields, we define permittivity for electric fields or components which attribute capacitance. So if a medium is having constant permittivity and Q and V are phasors, so we can directly use, or I mean Q and V can simply represent the RMS values in that particular notion when the medium is having absolute or constant permittivity. What is permittivity? We'll come to that in the upcoming few slides. So Coming back, simple, straight, parallel conductors. The conductor shown over here could be one strand in a composite conductor. We'll take up our discussion with with simple assumptions, and then gradually we will take up the case of multiple composite conductors, bundle conductors, etc., etc. The way we did inductance evaluation for single strand, group of strands, group of conductors, and so on. So what we have here is a single solid conductor, not a composite conductor, which analogously represents a overhead transmission line. It is straight, it is perfectly cylindrical, and its radius is small r, which is this radius marked over here. And this conductor is carrying current. Now, since this conductor is carrying current, so current flow, if I were to associate or understand, current flow in its basic definition is nothing but rate of flow of charges with respect to particular time. So basically, I is proportional to or equal to dq by dt. If current is flowing, which is usually the case for overhead transmission lines, and the transmission lines are usually carrying AC currents because we have the AC network in place usually. So if current is varying in time, it's definite for sure that if I is varying with time, which is proportional to or equal to dq by dt, if I is varying with time, then corresponding dq by dt would also vary with time. So it's imperative that q might also be a function of time, if not function of time, but at least it would remain constant. So if current is flowing, then it can analogously be represented as flow of positive charges, which is the usual theoretical definition of flow of current. The direction of flow of current is same as the direction of flow of positive charges inside the conductor. That's a different aspect, that positive charges actually don't flow. It's the electrons which sort of tend to dissipate around their mean position, and that's how energy or electrical energy is transferred. So, but we will not go into that. We'll assume for our sake of discussion that there is some conductor which is carrying current I, and if this current I exists, that means some charge will also be existing in that particular conductor for this current to exist. So we would assume that this charge which is present in the conductor because of this current I, we denote it to be an instant or a positive charge with q, small q as the notation, and c being the unit of the charge, which is coulomb. And our assumptions then again come in the way we took our assumptions for inductance, that there are no nearby conductors, there are no nearby charges which are perturbing or disturbing the charge distribution over here. So basically this charge is uniformly present. In fact, charges actually don't reside inside the conductor. If it is a perfect conductor, there would not be any charge inside the conductor. Entire this charge plus q would be residing at the surface of the conductor, not outside, but just at the periphery of this conductor, which is, let's say, plus q, and the quantum of this plus q which is present on the surface is effectively equal to the entire small q. So there are no nearby charges which are sort of perturbing this distribution of charge on the surface of the conductor. The conductor is a perfect conductor with all charges residing perfectly at the periphery. And as a result of this charge, there would also exist some electric field lines. These electric field lines are indicated by the red color arrows that you see. And it's the attribute of these electric field lines that if we have a perfect cylindrical conductor, and its its perfect surface, a cylindrical surface, then the electric field lines, they would be existing outside the conductor, which I have talked about quite a bit in the previous few discussions. Unlike magnetic flux lines, electric flux lines or field lines will not exist inside a perfect conductor. They would always exist outside the conductor because the charges are residing on the surface. Charges don't reside inside the conductor, unlike currents. And electric field lines, they would be outside the conductor as shown over here, and these electric field lines, they would be all radial and orthogonal. Since the charge density on the surface of conductor is uniform, so any point that I take or I tend to observe the electric field lines, since the charge distribution is uniform, there is no distortion which is happening because of nearby charges. So electric field intensity, which is denoted by this capital E, it's also going to be uniform around any point on the periphery, on the outside of the conductor, and electric field intensity unit is volt per meter. So with this electric field definition, let's now build upon gradually how capacitance can be evaluated. So if electric field lines exist outside the conductor, then we can also mark certain surfaces which we would call as equipotential surfaces, marked by the blue dotted circles. These equipotential surfaces mean that if I have to measure the potential at any point on this smaller circle, then no matter where this point is being taken on this smaller circle, again measuring the potential difference with respect to some reference, because potential difference, as the word difference is, it can exist between 2 points. It cannot exist only for one absolute point. If one absolute point potential has to be measured, then it has to be measured with respect to some reference, ground, neutral point, etc., etc. So when I say that I'm trying to measure the potential at any point on this smaller blue dotted circle, then at any point on this blue dotted circle, the potential value would be perfectly be the same. It would exactly be the same, and same would also be true for the larger circle, where the potential difference value might be different, but the quantum of V present over this surface would exactly be the same. So if I were to say, let's say this is V2 and this is V1, then V1 and V2, they need not be same. They have to be equal. They are unequal, and pardon me, they are unequal. And the reason why these potentials are uniform, or the surfaces are called equipotential surface, is because these equipotential surfaces are representing sections, or I would say they are representing surfaces which are again orthogonal to the electric field lines. And as I mentioned, that if the electric field lines, their intensity or quantum is same, because the charge distribution on the conductor surface is same, so no matter which point I take, the electric field lines have to be same. So if I take any surface which is orthogonal to this electric field line over here, or if I take the orthogonal surface at the same distance from the center of the conductor, let's say this is R1, this is also R1, R1 is different from R. If I am trying to measure or find a finding a orthogonal surface at the same distance from center of conductor along two electric field lines, where the electric field lines are equal in quantum, the directions are different, then since the field lines are having the same magnitude, the same intensity, that would mean that these orthogonal surfaces, their relative parameters would also be the same. And in terms of capacitance of electric field lines, that orthogonal surface is nothing but the potential or the voltage itself. So if these two surfaces were to have same attributes, that would mean that their voltages with respect to a common reference would also be the same. And that's the reason why if I draw any circle, concentric circle around the charged conductor, these surfaces would all represent the blue color circles, which are equipotential surfaces. So we consider one such equipotential surface at a distance x from the center of the conductor. So basically this green circle is having a radius of x, where x is definitely more than r, small r being the radius of the charged conductor. And we want to find what could be the potential electric flux intensity or field intensity at this surface if we know the quantum of E which is present over at a distance x from the center of the conductor. Then probably we can also find the corresponding value of the potential again with respect to some reference. So that is the basic idea. So basically we want to find what is the value of E of x at a distance x from the center of the conductor. So in order to find this electric field intensity, we choose elemental or a small surface which is marked by this element ds. ds is the surface area or elemental surface area along this cylindrical surface which we are considering, the cylindrical surface being the cylinder with cross section of radius x and the length of the cylinder being same as the length of the conductor. So that's why this green dotted line is also representing a cylindrical surface. If we were to be drawn on a 3D plot, then it would represent a cylindrical surface which would be parallel to the cross-sectional length of the charged conductor. That's the idea. So along this cylindrical surface, we want to find what is the electric field intensity at the surface of this equipotential surface. So ds is the corresponding elemental normal area vector or the surface area, and as per the dots which have been, as per the directions which you can easily observe, it appears that the ds vector, it is parallel to the electric field intensity vector. So basically E and ds, they are parallel vectors, and if we recollect, for two parallel vectors, if one has to take their corresponding dot product, then it is nothing but E magnitude ds magnitude into cosine of the angle between these two vectors. If there are two parallel vectors, the corresponding angle is perfectly 0 degrees. That would means this dot product of two vectors would simply be the corresponding magnitudes of the respective vectors. So with that, because essentially we'll be using this dot product, so I'm coming to that part in a moment. So coincidentally, E and ds are both orthogonal to the surface of radius x that we have considered. So the corresponding dot product becomes a simple scalar quantity. Please don't confuse or consider this cross to be the cross product. It is simply a multiplication factor, or represents the product of E and ds magnitudes. So with E and ds being parallel, E dot ds resulting into a scalar vector, there comes the beauty of Gauss's law, where the law says that along a surface or across a surface, if one has to figure out the net electric flux which is emerging out or protruding out of the surface, assuming that the surface is residing some charged conductor inside it, the surface itself need not be charged, but there is some charged body inside that particular surface along which this electric field line or flux line is to be considered. Then by Gauss's law, this electric flux line, which is nothing but the surface area or the surface integral of E dot ds, is nothing but equal to or proportional to the charge which is enclosed inside this surface. That's the beauty of Gauss's law. It doesn't say that this charge has to be at a particular location. Inside this surface, this charge could be present at the center. This charge could be present at any other random point inside the surface, but not on the surface, because we're trying to find the Gauss's law. So in fact, it can tend to be at the boundary of the surface, but again, the surface itself should not be charged, because we are not considering those specific cases. So inside this surface, this charge q, instead of being present over here, it could have been present over here, it could be present over here at any point. It need not be present at the center itself. So with this, since Ex dot ds is nothing but E into ds simply, and E being uniform, or E of x to be precise, E of x is uniform at any point I take along this cylindrical surface of radius x. So this surface integral can be simplified as surface integral of Ex into ds. Ex is same along any point I take on the cylindrical surface of radius x. So this can also be simplified as Ex with integral of ds. Es is a constant, it doesn't depend on the integral. So Es can come out of it, and Q is the net charge which is present over here. Epsilon naught is the absolute permittivity, whose unit, or it's a universal constant, absolute permittivity of free space, whose value is 8.854 × 10 to the power minus 12 farad per meter. Epsilon r is relative permittivity of the non-conducting medium, which is segregating out the charged surface and the charged body and the surface. So since it is we're talking about a transmission line, so around a transmission line, over a transmission line specifically, you would find ample amount of air. So epsilon r here indicates relative permittivity of air, which is equal to 1 because air is not a good conductor. And since the value of E of x is uniform, so this integral gets simplified into this form, where if we now focus on what is this integral, then this integral is nothing but the surface area or the curved surface area of the cylindrical surface which we have chosen. Again, remember, we are trying to find all our parameters with respect to per unit length of conductor. So if the conductor length is equal to 1, it could be 1 meter, 1 kilometer, 1 mile, depending on what units we have considered for distance. We are using it to be 1 meter by default for our sake of discussion. The conductor length is 1 meter, and if curved surface area, we recollect, the curved surface area of cylinder is the circumference of the circle, which is representing the curved surface area, multiplied by the length of the cylinder. Circumference is essentially 2 pi x because this circle is a perfect circle of radius x. So 2 pi x is the circumference of circle and 1 is the length of the conductor along which the entire surface area is to be found. So this surface area gets simplified into this, and now once we have ds elemental vector, so our E of x is a function of x, q by 2 pi epsilon naught into x v volt per meter square. Once we know what is this electric field intensity at the surface of of radius x, then we can also probably understand what would be this potential that we are trying to find, because once we know the potential, C is equal to Q by V. So once we know the potential, then probably we can also find the value of C, which is existing because of this capacitor, because of this charge Q. So potential difference in its basic definition or layman perspective is nothing but the work done to move a unit charge. A unit charge could be 1 coulomb, 1 microcoulomb, 1 nanocoulomb, depending on what unit is to be considered. It is the work done to move a unit charge in an electric field, in the presence of an electric field. So basically, if I were to explain, if I have two electric plates which are charged and air is in between these two plates, then if I intentionally capture out a positive charge of, let's say, 1 coulomb and move it from one plate to the other plate in between which there is an electric field present, then the quantum of energy dissipated or energy used to move this charge from one point to another between these two charged plates in the presence of an electric field would nothing be but the potential difference between these plates. So here Vij means I and j are two distinct points between which the potential is to be measured, and between these points I and j there definitely exists a non-zero electric field, and we are trying to understand how much work is being done to move a unit charge from point I to j in the presence of an electric field. If we were to overlap this discussion on the conductor that we have, then essentially we can choose two surfaces, two different equipotential surfaces, and that would give us essentially the potential difference between these two equipotential surfaces. And in this context, the electric field that we are talking about for potential difference to exist is because of the electric field intensity E of x, which is the force per unit charge, which we have evaluated over here. So if we know E of x, then we can also probably find the potential difference. So in order to find the potential difference, what we do is we take a hollow tube, hollow cylindrical tube whose width is dx, and this dx hollow tube is at a distance x from the center of this charged conductor. And as I mentioned, or as is told over here or discussed over here, potential difference is the work done to move the unit charge. So essentially, the incremental potential dV is nothing but product of E of x, which is the electric field intensity, multiplied by the width of the tube across which the potential is to be found. So since we know E of x, we substitute E of x, which is q by 2 pi x epsilon naught. Dx is the width along which the potential is to be found. Essentially, the charge is moving along this dx tube, and the work which would be done is equal to the field intensity multiplied by the shortest displacement or the width along which the charge is moving. It might happen that the charge is residing at the surface of x, let's say over here, and this charge, in order to move from this point or this surface to a surface whose width is x plus dx, the charge could move along this small hollow tube through lot of distances covered, but and essentially it reaches this point over here. No matter what the distance is traveled by the corresponding charge, the electric field intensity multiplied by the width, which is the shortest displacement or the shortest distance to be precise, displacement is the actual shortest distance, it would depend on the shortest displacement that would exist between these two surfaces. So that's the reason why dV is equal to Ex into dx. And now once we have known what is dV, we can take two such points or two such potential surfaces. We mark 2 points D1 and D2. There is a charge which has to move from D1 point to D2 point. As I was saying, it could directly go from here to here, the charge which is moving in the presence of electric field, or it can take any particular path in this manner and then also can reach D2. So no matter what the distance is covered, it is always the shortest displacement between these two potential surfaces. These two distances, potential surfaces, the radiuses are D1 and D2. So essentially the points D1 and D2, they indicate that they are the distance D1 from the center of the conductor, and the D2 point is again at a distance D2 from the center of the conductor. And since these points are along two individual equipotential surfaces, though actually the actual positioning of D1 and D2 doesn't matter. It is the radius of these equipotential surfaces between which the potential is to be found. So if dV is the incremental or unit potential difference, and we have to find the potential between D1 and D2, which is also equal to VD2 minus VD1. In certain textbooks or references, you may also find this to be equal to VD2 D1. But essentially, no matter what the context is, we are trying to find the potential difference between two surfaces, and that's the reason why there are two voltages for D2 surface and D1 surface. It would nothing be but equal to the integral of dV, and when we substitute dV in terms of x and dx, we have this expression of the potential, which is q by 2 pi epsilon naught natural log of d2 by d1. Now, once we know what is the potential difference, it is, as I mentioned, independent of the path traversed by the unit charge to move from 2 points on two equipotential surfaces. It is equal, it actually depends on the shortest equipotential displacement between these points, not the actual distance. And as you recollect, C was Q by V. Q is the reason why all this is existing. So once we know these 2 points D1 and D2, the capacitance between these points D1 and D2 would be Q by the potential difference, which is this beautiful expression in terms of farad per meter. Why do we have farad per meter? Remember, we had considered the conductor length to be 1 unit. So now if point D1 is exactly same or is residing on the surface of the conductor, remember, inside the conductor charges don't exist. This charge would exist on the periphery of the conductor. So if we have to move inside the conductor, then as I mentioned, inside the conductor charges will not exist. Charges will always be existing on the they'll always be existing on the surface of the conductor. I think I have erased that particular discussion. So if the charges exist inside, not inside the conductor, and they have to be present on the surface, if I have to find the potential inside the conductor, then as per Gauss's law, which says that the net electric flux which is emanating out of a particular surface is equal to or proportional to the charge present inside that surface. So inside a conductor, since charges won't exist, along this surface there would not be any potential or electric flux line at all. So The worst case point which D1 can take is the surface of the conductor itself, which is at a distance r from the center of the conductor, and D2 could be any point in general which is at a distance d from the center of conductor. So in that case, the effective capacitance at a distance d from the center of conductor would be this particular expression, where D1 is equal to r and D2 is equal to d. And remember or recollect, for inductance evaluation, we had seen the effect of skin effect. Over here, for capacitance evaluation, there is no deterioration or no change in the effective radius of the conductor, and hence capacitance doesn't result into skin effect. It's only the inductance effect which leads to skin effect and leads to increase in AC resistance. So now if we move on and try to complicate our discussion gradually, we have understood the capacitance evaluation for a single conductor. Now let's see how do we evaluate capacitance for single phase two wire system. Remember the discussions that we have for inductance evaluation, similar logic would be applicable here. We have two charged conductors, we have two current carrying conductors essentially. One conductor is acting as a return path for the other. So if we associate this in terms of the charges, so if Q1 is existing on one conductor, at the same point of time the other conductor should have the negative charge of it, and that's how the current balancing would happen, because it's a single phase two wire system where one wire is acting as a return path for the other conductor. So the distance d between these two charged conductors, it's very high compared to individual radiuses r1 and r2. The electric field distortions are not happening. Q1 and Q2 are perfectly distributed along the respective surfaces. There is no distortion in this charge density or surface over here. The effect of earth or ground is neglected for time being. So if we apply the similar logic of finding potential, which is V d1 d2, the one which we discussed over here, and try to understand the potential difference between two such charges, since our focus is to find the potential between 2 points. Point number 1 is the center of conductor, which is point number 1. The other point is point number 2, which is the center of conductor of charge Q2. We have to find the potential difference between points 1 and 2, which are the center of the conductors, because of charges Q1 and Q2. So if we find the potential difference because of charge Q1, then there's a little bit of a suggestion here. If we choose 1 as our first point of reference for measuring displacement for point number 2, and the charge that we are looking at is charge Q1, then it's obvious that since we're talking about charge Q1, so in potential difference expression, Q1 would appear here because there is no other charge apart from Q1 in this particular expression to be talked about. The distance that would appear in the natural log term, the numerator is always the distance between the actual position of charge Q1 and the second point with which the potential is being measured. So if we talk about Q1 at a distance from conductor Q2, the actual distance is d. And so the numerator would always refer to the distance between charge Q1 and the second surface, whereas the denominator in the natural log term would refer to the distance between the actual charge and the first point between which the potential is being measured at. So if we just keep that aspect in mind, because that was how we evaluated our potential difference expressions, then the overall discussion would become simpler. So we have two such charges, Q1 and Q2, so we would have two such potential differences. One is V12 because of charge Q1. Similarly, we would have V21 because of charge Q2. The expressions look similar, only difference is in terms of the charges themselves. And since Q1 is negative of Q2, so V12 Q2, which would be negative of V21 Q2. Why? Because V12 Q1 is nothing but V2 Q1 minus V1 Q1. Similarly, V21 Q2 is V1 Q2 minus V2 Q2, which is also equal to minus of V2 Q2 minus V1 Q2, which is also equal to minus V12 Q2, and that's how this negative term is coming in. And since Q2 is equal to minus Q1, so V12 Q2 is this expression itself. Since the potentials are existing because of two different charges, so the effective potential difference between these wires would be the additive sum of these two potentials. So if we add those two, then it would actually come as, it would actually be equal to, uh, just give me a moment. So let's do that. So we have V2 Q1 as Q1 by 2 pi epsilon naught natural log of d by r1. We have V12 Q2 as Q1 by 2 pi epsilon naught natural log of d by r2. And remember, when we add these two terms where the first terms are common, the natural log terms, the arguments of natural logs, they get multiplied, and that's how you get d square by r1 r2. Once we know V12, we can use the same capacitance evaluation because the effective charge is Q1 or Q2, which is negative of Q1. So C12 is Q1 by V12, which gives us this expression in terms of farad per meter. Often it is convenient to find capacitance not between line to line, but between line and phase, or phase and the neutral point. So if we look at this particular arrangement of Q1, Q2, and the distance, and since Q1 is equal to minus Q2, so for Q1, if I were to draw the electric field intensity line, then it would be orthogonal to this surface, whose quantum would, let's say, be E1. And similarly, I would have E2 electric field coming out, which would be E2. And these are all orthogonal. And since Q1 is negative of Q2, it would mean that E1 would be negative of E2. So if I talk about a point which is at midpoint from these two surfaces, the effective electric field intensities, they cross out. So there comes a point in between these two current carrying charges or current carrying conductors or charged conductors, where the potential difference would be perfectly zero, and we can denote that point to be a neutral point or a zero potential point. And remember, unlike resistance and inductance, when they are in series, their corresponding sums or individual inductances get added up. If they are in parallel, then the effective inductance is inverse of inverse sum of the inductances. The similar vice versa logic is applicable for capacitances. If I have two capacitances in series, then the effective capacitance in terms of C12 would be 2 times of C12. Since C12 is pi by epsilon naught, so our capacitance or phase capacitance is this particular expression, which is 2 pi epsilon naught divided by natural log of d by square root of r1 r2 farad per meter. Coming to a much more complicated system, which is multi-conductor system, where we have n conductors carrying currents or carrying different charges. These charges could be different from Q1 to Qn. Their radiuses are also different from R1 to Rn. And these conductors are at different large spaces. The space between them is particularly large, so there is no distortion of charge on the surface of individual conductors. There is no distortion in terms of electric fields. And the distances, they are marked as D12, D2n, D2j, etc., etc. We want to find the potential difference between center of charge conductor I and between the center of charge conductor J. We want to find the potential difference between these 2 points I and J with respect to all possible charges that are present inside this particular arrangement. So if you remember, if I were to find Vij with respect to Q1, so Q1 being the single sole charge, that would come over here, and around these conductors there is all air, there is no other medium, so epsilon r is perfectly 1. In the natural log term, the numerator should be the distance between position of charge Q1 with respect to center of conductor, which is carrying charge Qj. So the first distance that should come is d1j, which is the term present over here. And the denominator should be the distance between Q1 and the conductor, which is numbered I. And that's how d1i comes in, which is a denominator over here. If we apply the same logic, we can also find the potentials with respect to other charges. For charge I or j, dii and djj could refer to ri or rj respectively. They are the self radiuses. And with all these individual potentials, we can find the apply superposition theorem and find the overall effective potential, which is the summation of all individual potentials with respect to the individual charges. That's all for today's discussion. We will take up our next discussion on capacitance of three-phase lines and effect of earth based on the multi-conductor potential difference discussion. Thank you.